So far in this module, we've been modeling electrical circuits as differential equations. If you recall, an alternative mathematical model is a transfer function. So an alternative approach is to model the circuit directly in the Laplace domain. When we do that, we will use something called complex impedance. Impedance is a similar concept to resistance, and for resistors, impedance and resistance are the same. For capacitors and inductors, however, impedance changes with frequency, and so that's why it's a more complicated concept that's needed. We can't really speak about the simple resistance of an inductor or a capacitor. The frequency dependence of this quantity won't make a lot of sense to us now, but it's something that we'll try and come back to later in the semester. In this analysis, we can treat complex impedances like we did resistances previously, and the reason that we can do that is the definition of impedance has a similar relationship to Ohm's law. So whereas resistance was voltage divided by current, impedance is also voltage divided by current, except here there's the voltage and the current aren't constants, they are dependent on frequency. Because of this adherence to an Ohm's-like law, we can also combine the impedances of components in series and in parallel the same way that we generated equivalent resistances of resistors in series and parallel. So now we want to define what the impedance of our three different components are. So starting with resistors, we'll take the Laplace transform of Ohm's law, the time-based relationship between voltage and current. E becomes E of S, I becomes I of S. R is just a constant, so it comes out front. Complex impedance is voltage divided by current, which in this case, if we take this current and divide it to the left-hand side, we will find that impedance is just equal to resistance. Therefore, the impedance of a resistor is equal to R. Now we will do the same thing for capacitors. Recalling the relationship between voltage across a capacitor and current through a capacitor, we have this integral-based relationship. Recall our Laplace transform property that states that integration in the time domain becomes division by S in the Laplace domain. Therefore, we have this expression E of S equals 1 over C times I of S over S. Again, to get the impedance, we need to divide through by I of S. And then we get the complex impedance of a capacitor is equal to 1 over C times S. Finally, we perform the same sort of action for an inductor. Voltage is equal to inductance times the time rate of change of current. Recall the property that differentiation in the time domain becomes multiplication by S in the Laplace domain. We divide through by I of S to get that complex impedance is equal to S times L. So in essence, we just need to memorize these three sort of properties, or these three definitions of complex impedances for our three different types of components. But also keep in mind that we're implicitly assuming something when we did this. And what we're assuming is that the initial conditions are 0. So when we took the Laplace transform of this derivative, we're basically assuming that the current through the inductor was initially 0. And when we took the Laplace transform of this integral, we're basically assuming that the initial value of the integral was 0. That is, there was no initial charge on the capacitor. So here's a circuit that we addressed earlier that we found the governing differential equations for. We found one equation for each loop. From those differential equations, we could find the transfer function EO of S divided by EI of S. And the way that we do that is we take the Laplace transform of the differential equations and then do some algebra in order to get it into the form output over input. that process would actually be somewhat tedious, the algebra involved. It's actually much simpler to derive the differential equation directly using complex impedances, and so we'll go ahead and demonstrate that approach here. So the first thing we need to recognize is what are the complex impedances of the individual components. So if you recall, the complex impedance of a resistance, of a resistor, is just its resistance. So the impedance of this resistor is just R1. Recall what the complex impedance of an inductor is. You can look back on the previous slide, but it's equal to S times L. Then this resistor again, impedance is equal to resistance. And then finally we have the impedance of the capacitor, where again, if you look back on the previous slide, you can see that the impedance is equal to 1 over C times S. We then want to simplify this, and we can use these properties of how to reduce or how to find the equivalence of components in series and in parallel. We'll go ahead and define this resistor to be Z1, have impedance Z1. These two components, the inductor and the resistor R2, are in series. And so if we recall back to how to combine resistors in series, you recall that the resistance is sum. So using that same idea, the impedance is sum. So the impedance of this branch with these two components in series is SL R2. We can then notice that this branch is in parallel with this branch. And if we recall, the equivalent resistance of two resistors in parallel is each individual resistance, the inverse of each individual resistance summed together, and then the inverse of that complete sum. So I will call the equivalent impedance of these two branches in parallel Z2. We'll have 1 over the impedance of the first branch, which is those components in series, which we found to be SL plus R2. And then we'll add that to the inverse of the impedance of the capacitor, the other branch, whose impedance is 1 over CS. And then that total is also inverted. If we're dividing by a fraction, you may remember that that's the same as multiplying by its reciprocal. So the reciprocal of 1 over CS is CS. In order to combine these two inner elements, they need to have a common denominator. So in order to combine them, we need them both to have a denominator of SL plus R2. In order to achieve that, we need to multiply CS by SL plus R2 and divide it by SL plus R2. Once they have a common denominator, then we can just add the numerators. So the denominator is SL plus R2. The numerator is 1 plus, if I go ahead and distribute, I get C L S squared plus C R2S. And then if I invert that, I get that Z2 is equal to SL plus R2 divided by CL S squared plus C R2S plus 1. So we've taken a relatively complex circuit and simplified it into the form that I'm going to show you on the next slide, where I have a single impedance Z1 in this location and a single impedance Z2 in this location. If you look at this, you may recognize it as having the form of a voltage divider. A voltage divider is much simpler, and we can determine a transfer function for this simpler equation, this simpler circuit. I'm going to make the assumption that the current is equal to I and it flows clockwise around the circuit. If you recall, a transfer function that we're trying to find is E(O) of S divided by EI of S. It's basically the Laplace transform of the output divided by the Laplace transform of the input. If we look at EO, the voltage EO, it's the voltage across Z2, where the current through Z2 is I. Thinking back to the definition of complex impedance, voltage has a similar relationship to that we had with Ohm's law. Voltage is equal to current times impedance. So EO is equal to I of S times Z2 of S. The voltage input, however, spans both Z1 and Z2. So it's as if we were looking at this, EI is equal to the drop across Z1 plus the drop across Z2. Another shortcut is to think of Z1 and Z2 as being in series with one another. Therefore, the voltage EI is equal to the impedances summed together, because that's how you combine impedances in series, multiplying the current, which is also I, which is the same as the current through the output. Looking at this, the current I of S cancel, and so our transfer function is equal to Z2 divided by Z1 plus Z2. From the previous slide, we had expressions for Z2 and Z1. So the expression for Z2 was it had a numerator of SL plus R2, and then it had a denominator of CL times S squared plus C R2 times S plus 1. So our transfer function has Z2 in the numerator, and then it has Z1, which again, if you look back on the previous slide, is equal to R1, plus Z2 again, which is the same as the expression that we have in the numerator. S times L plus R2 divided by CL times S squared plus C times R2 times S plus 1. In essence, this is the transfer function, and we could stop here. But in general, we would like to clean up our transfer function a little bit so that it's easier to understand and compare. And so basically, I would like you to get your transfer functions into a form of a polynomial, a single polynomial divided by a single polynomial. So in essence, we want to get rid of these fractions here. And the way that we can do that, the way that we can clear them out, is to multiply through by the denominator. So if we multiply through by this denominator, CL S squared C2 R CR2S plus 1. Do the same thing down here. CLS squared plus CR2S plus 1. Then we can clean this up. So if we distribute this through, this denominator will cancel with that expression. We'll be left with SL plus R2 in the numerator. In the denominator, if we multiply through, this expression will distribute and it'll multiply the R1. And then when we distribute it to the second term, this denominator will cancel with that term, and we'll just be left with SL plus R2. Now this is done. So we've gotten the transfer function, we've reduced it into a form of a single polynomial divided by a single polynomial. We could stop there, or we could distribute the R1 and gather like terms. So I'll go ahead and do that real quickly. Our numerator is SL plus R2. If I distribute this R1, I'll have R1 times C times LS squared. If I distribute the R1 to this term, I'll have an S term, and I've also have this S term. So I have C times R1 times R2 plus L, where I factored out the S. And I distribute this R1 times 1, that'll be a constant, and then I'll have this R2, which is a constant. This is the final form of our transfer function. That may not have seemed very easy, and it may not have been for the first time that you've seen it, but these sorts of approaches for clearing out fractions, clearing out denominators, and gathering like terms and simplifying is something that we'll do with some regularity, so it'll become easier. And it's actually significantly simpler, the algebra that we had to do here, than if we had started from the differential equation, taken the Laplace transform, and then done a bunch of algebra. One thing to be aware of is that this approach is only valid if the initial conditions are 0, as is the assumption when we find a transfer function. Recall that when we derive a transfer function, we make the assumption that we're not including the initial conditions in the model, or we're assuming that the initial conditions are 0.